Have you ever looked up at the night sky on a clear, dark night and wondered what those little pinpricks of light truly are? Those distant suns shining across unimaginable distances? Or perhaps you've pondered why the moon, our celestial neighbor, seems to change shape throughout the month, cycling through its phases. For thousands of years, humans, driven by an innate curiosity, have looked to the heavens and asked these very questions, seeking to understand our place in the grand scheme of things. This quest for understanding, this relentless pursuit of knowledge, is driven by curiosity, the very heart and soul of physics. Physics, at its core, is the story of us, of humanity itself. It's our collective effort to understand the fundamental rules that govern the universe, from the smallest particles to the largest galaxies. It's not just about complex equations and abstract theories. It's fundamentally about discovery, about uncovering the secrets of nature, insight, and ultimately about understanding our place, our significance in the vast and awe-inspiring cosmos. When you throw a ball, observing its arc and trajectory, or feel the comforting warmth of the sun on your skin, you're directly experiencing physics in action, witnessing its principles unfold in the everyday world around you. Understanding physics is like possessing a secret manual, a comprehensive guide for deciphering the workings of the universe, revealing the hidden connections and intricate patterns that exist everywhere, from the smallest atom to the largest star. Our journey through the world of physics will take us from the musings of ancient thinkers and philosophers to the cutting-edge research conducted with today's most powerful machines and sophisticated instruments, meeting the brilliant minds, the courageous individuals who dared to question established norms and embark on paths of discovery. This is fundamentally a human story, a story filled with mistakes and missteps, groundbreaking breakthroughs that reshaped our understanding, and the sheer, unadulterated joy of witnessing something new, of glimpsing the universe in a way no one ever has before. So let's embark, let's board our ship of imagination and set sail, and together we'll witness the remarkable discoveries that have not only changed the course of physics, but have also profoundly shaped our world and our understanding of it forever. Our journey begins in ancient Greece, a land of vibrant culture and groundbreaking ideas. It was there that pioneering thinkers first began to use logic and careful observation to question the very nature of the world around them, daring to challenge long-held beliefs. One of the most fundamental questions they grappled with was the Earth flat, as many assumed, or could it be round? Aristotle, a keen observer, noticed that ships disappearing over the horizon did so hull first, suggesting a curvature. He also noted the Earth's round shadow cast upon the moon during lunar eclipses, compelling evidence that our planet was, in fact, a sphere. But Eratosthenes, a brilliant mathematician, took it even further, seeking to quantify the size of this sphere. By ingeniously comparing the lengths of shadows cast in two different cities at the same time, using only basic geometry, he calculated the Earth's circumference with remarkable accuracy, a feat of intellectual brilliance. These Greeks, in many ways, were the first physicists, laying the groundwork for scientific inquiry. They demonstrated the power of observation, showing that we can question, observe, and use reason and logic to find our way to a deeper understanding of the universe. They held a profound belief that the universe was not chaotic, but rather followed consistent, discoverable rules. This core idea, that the cosmos is fundamentally knowable and understandable, was perhaps their greatest and most enduring gift to humanity. It sparked a vibrant tradition of intellectual inquiry, a thirst for knowledge that would echo through the ages. This tradition would eventually ignite the scientific revolution, transforming our understanding of everything. In essence, the Greeks set the stage for all future scientific discoveries, providing the essential tools for exploration. Their insatiable curiosity, coupled with their emphasis on logical reasoning, became the very foundation upon which modern science is built. And so, the incredible journey of physics, our quest to understand the universe, truly began with these remarkable thinkers. For centuries, people believed Earth was the center of everything, with the sun and stars revolving around us. Copernicus challenged this, suggesting the planets orbit the Sun, a radical idea. Galileo, using a telescope, saw the Moon's craters and Jupiter's moons, proving the heavens were not perfect and that not everything orbited Earth. His discoveries shattered old beliefs and showed the power of observation. Galileo's courage to trust evidence over tradition started a revolution in science. He taught us to look, question, and test, even if it meant challenging authority. The universe became a place we could study and understand. Galileo's work opened the door to a grander vision of the cosmos. The stars were no longer distant mysteries. They were worlds to explore. Science would never be the same. The cosmos was within reach. After Galileo, Isaac Newton took the next giant leap. He wondered if the force that pulls an apple down is the same that holds the moon in orbit. Newton's law of universal gravitation revealed that every object pulls on every other, with a force depending on mass and distance. He also created the 3 laws of motion, forming the foundation of classical mechanics. Suddenly, we could predict the movement of everything from baseballs to planets. Newton's laws made the universe seem like a giant, understandable machine. His ideas dominated physics for centuries and are still essential today. Newton showed us the universe is ordered and knowable. We could now calculate, predict, and explore with confidence. The cosmos had a rulebook. In the 18th and 19th centuries, physics expanded to invisible forces: heat, electricity, and magnetism. Scientists like James Joule showed that heat and motion are forms of energy, leading to the law of conservation of energy. Energy can't be created or destroyed, only transformed. James Clerk Maxwell unified electricity and magnetism into electromagnetism with 4 elegant equations. He revealed that light itself is an electromagnetic wave, connecting electricity, magnetism, and light. Maxwell's theory predicted other waves: radio, microwaves, X-rays, central to modern technology. The concept of energy unified many mysteries of nature. Physics now explained everything from steam engines to lightning. The invisible became understandable. This era powered the Industrial Revolution and our modern world. The age of energy had begun. By the dawn of the 20th century, the world of physics was on the cusp of a revolution, a transformation that would challenge the very foundations of our understanding. Physics, as defined by Newton and his successors, seemed complete, a well-oiled machine explaining the motion of planets and the behavior of matter. It was an era of confidence, but beneath the surface of this apparent perfection, small problems remained, tiny cracks in the edifice of classical physics that hinted at a deeper, more complex reality. Enter Albert Einstein, a young patent clerk working in Bern, Switzerland, a man with an insatiable curiosity and a mind that dared to question the established order. He saw these seemingly insignificant problems not as mere anomalies, but as clues, whispers of a deeper reality waiting to be uncovered, a reality far stranger and more profound than anyone had imagined. In 1905, a pivotal year in the history of science, he introduced special relativity, a groundbreaking theory that would forever alter our perception of space and time. At its heart lay 2 revolutionary postulates. The laws of physics are the same for everyone moving at constant speed, regardless of their relative motion, and the speed of light in a vacuum is constant for all observers, regardless of the motion of the light source. This seemingly simple idea had profound consequences. It meant that time could slow down, a phenomenon known as time dilation, and space could shrink, an effect called length contraction. Time and space are flexible, not absolute, as Newton had believed. They are intertwined, forming a single entity called space-time. His famous equation, E=mc², the most recognizable equation in the world, showed mass and energy are 2 forms of the same thing, interchangeable and fundamentally linked. This explains the sun's power, the source of its seemingly endless energy, and the energy locked inside atoms, a force that could be unleashed with devastating consequences. In 1915, after years of intense work, Einstein unveiled general relativity, an even more radical theory that redefined our understanding of gravity. Gravity, he proposed, is not a force, as Newton had described, but the bending of space-time by mass. Massive objects warp the fabric of space-time around them, creating what we perceive as gravity. Planets orbit the Sun not because they are pulled by a mysterious force, but by following curved paths in this fabric, paths of least resistance in the warped geometry of space-time. Gravity, in this view, became the shape of the universe itself, the cosmic architecture that governs the motion of galaxies and the evolution of the cosmos. Einstein's ideas transformed our understanding of reality, ushering in a new era of physics and cosmology. Space and time were no longer fixed, immutable entities. They could bend, stretch, and warp under the influence of gravity, creating a dynamic and ever-changing universe. The universe, as revealed by Einstein, was far stranger and more beautiful than ever imagined, a cosmos of warped space-time, black holes, and gravitational waves. While Einstein explored the vast, others probed the tiny world inside atoms. J.J. Thomson discovered the electron. Rutherford revealed atoms are mostly empty space with a dense nucleus. But classical physics couldn't explain why atoms are stable. This led to quantum mechanics. Energy comes in tiny packets or quanta. Electrons can only occupy specific energy levels, like steps on a ladder. In this quantum world, particles behave like waves, and certainty gives way to probability. You can't know both a particle's position and speed exactly. Sometimes things exist in multiple states until measured. Quantum mechanics, though bizarre, is incredibly successful. It underpins chemistry, materials science, and all modern electronics. The strange became the foundation of our technological world. With relativity and quantum mechanics, physicists could finally ask, where did the universe come from? In the 1920s, Edwin Hubble discovered galaxies moving away from us. The universe is expanding. Run the clock backward, and everything was once packed into a hot, dense point, the Big Bang. The theory predicted a faint afterglow, the cosmic microwave background. In 1965, Penzias and Wilson accidentally discovered this ancient radiation. It was the echo of the universe's birth, confirming the Big Bang. We were not just seeing stars, but hearing the universe's origin. The cosmos had a beginning, and we could finally study it. Physics had become a tool to explore the entire universe. Our journey has taken us from ancient Greece to the edge of the universe. We've learned the rules of motion, the nature of light, and the secrets of atoms. Yet, our two best theories, relativity and quantum mechanics, don't work together. The next challenge is a theory of everything, uniting the big and the small. Mysteries remain. Galaxies spin too fast, hinting at invisible dark matter. The universe's expansion is speeding up, driven by mysterious dark energy. Together, dark matter and dark energy make up 95% of the universe. We barely know what they are. The future of physics lies in exploring these unknowns. The greatest discoveries are still ahead. The cosmic quest continues.